All right, so today we are in Unit 11, Day 1, and we are talking about geometric sequences. The first learning target is I can recognize and extend geometric sequences, and the second is I can find the nth term of a geometric sequence. Okay, let me just pull my calculator up. So, a couple vocab words. A geometric sequence is a sequence of numbers where the ratio of consecutive terms is the same number, or called the common ratio. Okay, consecutive terms means terms that are next to each other, right next to each other. Okay, so here is an example. I've got 3, 6, 12, 24, and then it's going to continue on and on and on. Okay, this is a geometric sequence. So first, let's calculate that common ratio. So in order to find the common ratio R, in blue you can see you can calculate the value of R by dividing each term by the one before it. Okay, so I'm going to work backwards. I'm going to 24 divided by 12 to see what that is. And when I do that, I get 2. Okay, I can't just do 1 though. I need to go all the way through to make sure that it's consistent, right? Because it must be common, must be the same number through all of them. So now I do 12 divided by 6, and I also get 2. And then I do 6 divided by 3, and I also get 2. Okay, so that means my common ratio R must be 2. So I divide backwards in order to get that common ratio. Then it says calculate the next 3 terms. So what I'm going to do then in order to get the next 3 terms is, if I am going up, right, I'm going to be multiplying by 2. Right? If I go backwards, I'm dividing by 2. So when I go forwards, I'm going to multiply by 2. Okay, so in order to do that, I must times 2. That gets this spot. Times 2 gets me second one. And then times 2 gets me the third spot. Okay, so we're just going to multiply through to get that. So we start with the last term is 24. We're going to multiply by 2, and we get 48. And then we multiply that by 2. I can just hit times 2, and I get 96. Then I can multiply by 2 again, and I get 192. 48, 96, and 192. And that's how you calculate the next 3 terms. And then you could put a comma and a couple more dots because it's going to keep going on. All right, so next, geometric sequences can be thought of as functions, where functions have an input, which represents the term number, and the output, which represents the term itself. Okay, so for example, the position in the sequence, right, would be my input. So the first position would be 3. Okay, so that's kind of how we think about it. Okay, the second position would be 6. The third position would be 12, and the fourth would be 24. Okay, so then we also use these like subscripts that I've got on this last line, and that also represents the term number. So it would be the first term, right, is my subscript. Okay, and when it's small and below, we call it a subscript. So my second term, right, would be 2, and so forth and so on. So if I did a 27, this would be my 27th term, or the 27th position in the sequence. So now what we're going to do is we're going to find the common ratio, and we're going to find the next 3 terms. So we're going to skip example 1, and we're going to do example 2 because we're going to be dealing with some negatives, so I can show you how to find that. Okay, So in order to find the common ratio, what you need to do is you need to divide backwards, right? So I want to take 1/4 and I want to divide it by 1 to find that common ratio. So I'm going to do 1/4 in parentheses, 1 divided by 4, 1/4, and I'm going to divide that by -1. And when I do that, I get -0.25. Okay, now I have to make sure that that is consistent when I divide through the rest of my sequence. So then I do -1 divided by 4, and I get -0.25. And then I go again, 4 divided by -16, and I get -0.25. Okay, so that is consistent, which means my R is -0.25. Okay, so in order to get the next 3 terms, in order to go forward, I'm going to multiply by 0.25, by -0.25, right, to get the next term. And then I multiply again to get the next term, and I multiply again to get the next term. So we're going to start with 1/4, and we're going to multiply it by -0.25, okay? And it gets that decimal. I can convert my decimal back to a fraction by pressing math, and then enter, enter. I get -1/16. Okay? Then again, I'm going to multiply that. Just hit multiply by -0.25. And I'm going to get the decimal, and then I can convert that back to the fraction, +1/64. Okay, and then my next term, multiply by -0.25, and I get that decimal, convert it back to a fraction, -1/256. Okay, so that's how you find the ratio and the next 3 terms. What if I wanted to find the 14th term? Well, let's see what I've got. I've got a⁻1, the first term, a⁻2, the second term, a⁻3, the third term, and a⁻4, the fourth term. Okay, well, in order to get a⁻5, right, I'd have to multiply by my common ratio. Okay, let's go backwards to calculate that. So I want to do -40 divided by 20, and I think it's going to be -2. Now let me make sure that that works. 20 divided by -10, -2, and -10 divided by 5. So the common ratio is going to be -2. Where should I write that? So then I would need to go forward a ton of spots, right, until I got the 14th term. So I'm going to start with the last one, -40. I'm going to multiply that by -2. This is the 5th term, the 6th term, the 7th term, 8, 9, 10, 11, 12, 13, and 14 times. I had to hit enter in my calculator. I get -40,960. Actually, that was the 14th, right? Not the 15th. Okay. All right, so I could do that in my calculator, but it wasn't that bad, right? I mean, there's only 14 terms, but what if it was something even bigger, okay? Is there an easier way to do this? Is there a formula? Well, yes, there is a faster way, and it's called the function rule, okay? So basically, we're making an equation in order to calculate any position in a geometric sequence. So the function rule, a⁻n, okay, this is like generic for any term number n, right? I've got my a⁻n, where n represents some term number, okay? And then that's equal to my first term, and let's write the function rule for this example. So the first term in this example, whoa, it's moving so slow, is 5. Okay, so I would plug that in for my a⁻1. Okay, and then the ratio we calculated was -2. And then because we're just writing the formula, because we're writing the function rule, I'm just going to leave it as n minus 1. Okay, then I could plug in values for n and actually calculate different terms. All right, so that's what I'm going to do with this next one. Okay, I've got a sub 14, okay, where 14 is my n. So I take my formula, so I've got 5 times 2, -2, and then in the exponent, I've got n minus 1. Well, my n is 14, so 14 minus 1 is 13. And now I plug that into my calculator, and I see what I get. So I've got 5 times -2, oops, to the power of 13. And we get -40,960. Okay, so that was a lot easier, and I could do that for the 100th term, the 200th term, and so forth, and continuing on. Okay, so we think about it, well, why is it to the 13th power instead of the 14th power? I want to think about how many times did I multiply by 2. So first, I started with A1, so I multiply by 2, multiply by 2, multiply by 2, multiply by 2, so that's 1, 2, 3, 4. Right, is that where we started in our calculator? I want to go back to -40. Right, oops, no, stop, okay. So right here, that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, I multiplied by 2 13 times, right? So that's why I've got 2 to the power of 13. So now let's try. We're going to start off by writing a generic function rule, and then we'll actually calculate the term number. So I'm starting off with my a sub n, and then we're going to get some number, some rate, and then remember, I'm going to have my rate, my common ratio, to the power of n minus 1. That's the rule, the general function rule. So for this example, the first term is 1/28. Okay, so that is my a sub 1. The common ratio is 0.5. That is my r. And I'm going to take those and put those in. So I've got 1/28 is in front of the parentheses. 0.5 is in the parentheses. And then to the power of n minus 1. Right? That's the generic function rule. So if I wanted to calculate a sub 10, then I would take 1/28 times 0.5, and then my n is 10. So n minus 1 is 9. And let's plug that into our calculator. So I've got 1/28 times 0.5 to the 9th power. And I get 0.25. That's my answer. So that means the 10th term would be 0.25. Okay, lastly, I've got an example of a table. It says the table shows a card's value for 3 years after it's purchased. The values for a geometric sequence. The values form a geometric sequence. So we could think of this as like a sub 1, a sub 2, a sub 3, or we could think of it as like 10,000, 8,000, and 64,000, right? And it would continue on. How much will the car be worth in the 10th year? Well, that would be like calculating a sub 10. All right, so before we can even do that, we need to find the ratio. So we divide backwards in order to find that ratio. So I'm going to use my calculator, just like what we've been doing, just bigger numbers. I'm going to take 6,400 and I'm going to divide it by 8,000. And I got 0.8. Okay, so let me check. Do 8,000 divided by 10,000 to make sure that I get 0.8. So the common ratio is 0.8. Okay, my first term, my a sub 1 is 10,000. So let's take this and let's write a function rule. Okay, so our function rule, a sub n is equal to our first term is 10,000 times the rate, 0.8 to the power of n minus 1. Right? Now let's calculate the 10th term, because that's what it's asking for after the 10th year. So a sub 10 is equal to 1,000, or 10,000 times 0.8. And then if n is 10, n minus 1 is 9. Okay, let's see how much it's worth in its 10th year. So I do 10,000 times 0.8 to the power of 9. And I get 1,342. And we're thinking about dollars, we would round to the nearest cent. So 0.18, 1342.18. Right, and we're thinking in terms of money. Okay, so the car is worth that much in 10 years. All right, and that is our intro to geometric sequences.